Continuing our efforts to classify matter, we're going to talk about mixtures. So a mixture is matter that can be separated into its components via physical separation. So if you remember, compounds were separated by chemical separation. Mixtures are separated by physical separation. One of the things we can start to see a lot of these rules, how people figured out the types of matter, they tried to break them apart. What is it made out of? Again, they were asking questions. So physical separation, any process where substances are not transformed. So this is how mixtures are separated. Examples could be, here you have a mixture of salt and pepper. You could physically grab those different pieces. You can grab your pieces of salt, grab your pieces of pepper, use a very tedious process with tweezers, and move them apart. But importantly, you can do this without having to change the fact that one is salt and one's pepper, right? You can just literally grab them. You don't have to change what any of it is. You don't turn the salt into sodium and then make them, in terms of separating them apart. Filtration is a really common way that we separate solids from liquids. Again, here, if you, say running a coffee filter, you have, say, wet coffee grinds, and what happens is the liquid flows through. But you haven't changed what the liquid is. It's the same exact liquid that was in the solids. It's just flowed through the filter, whereas the solids didn't. You can also boil off. So if, say, this is one of the ways you can remove, say, water from salt. If you have, say, salt water, you just boil it. The water all leaves, and you're left with salt. But importantly, this is the same salt that was in the water, dissolved in the water. It's just no longer mixed in the water. So mixtures can be separated via physical separation. And really, what that means is basically they are a combination of two or more substances. So if you take two substances and you mix them together, you physically mix them together, you don't form a new substance, you just keep those two substances mixed up, that's how you lead to a mixture. And so one of the most important property of mixtures is that they have variable composition. If you remember, substances were always the same. You always made them in the same way. Mixtures are not made in the same way. You have control, so you can make chicken soup is a mixture. You can make that in all sorts of different ways. You could say, you can't find any carrots. Boom, you don't use carrots this time. We'd still call it chicken soup, but it has a different composition. Same with, say, salt water. Do you put a lot of salt in the water, or do you put very little salt in the water? Right? Those variable composition. Functionally, mixtures are all the samples of matter you interact with on a day-to-day basis. One of the things is just kind of more useful because of that variable composition. You can control the properties of a mixture, but also, it's just really hard to keep things pure. Kind of passively, things tend to get mixed up. If you think of like the cleanliness of your house, you have to work to keep things separated out. They just kind of passively mix on their own. Within mixtures, there are two types, heterogeneous mixtures and homogeneous mixtures. And what this has to do with is a question of how evenly mixed something is. So something that's a heterogeneous mixture, this hetero means different. So these are mixtures whose composition varies. So if we look at these two solids, granite is a heterogeneous mixture. We can see that the composition varies because we can see different colors in there, right? There's dark bits, light bits, brown bits, all sorts of different colors. You can think that if you were to touch it, it would feel rough because there's different kind of bits that are floating around in there. There are definitely different substances. You can see the different colors, and they're not mixed evenly. The composition varies depending on where you look in the piece of granite. It's going to affect what substance is present. A homogeneous mixture, like this sample of brass on the other hand, is going to be the same throughout. Homo and homogeneous means same. And so you have constant composition throughout. It doesn't matter where you were to look in the sample of brass, you would see the same mixture of the different substances present. There's no necessarily like more of, say, one type of metal that's mixed in the alloy in one part or the other. Brass homogeneous, granite's heterogeneous. One of the things about homogeneous mixtures, brass, if you didn't know that this was a mixture, it would look like a substance because it looks like it has all the same properties. The important aspect is how you can know it's a mixture is because there's more than one way to make brass. It has variable composition. So a lot of times classifying matter is going to require you to know something about it. You know, how was this made? Did you see it made? Is there control over how it's made? Did you just kind of pour things together? Those sorts of things, those sorts of factors inform if it's a mixture and then what type of mixture it is. So let's look at some examples of parsing out whether or not something is homogeneous or heterogeneous. So I have my three mixtures. It is chicken soup, salt water, and blood. And so we want to think about, are these things homogeneous or heterogeneous? So it's a given that these are mixtures because there's different ways to prepare them. And so then the question is it homogeneous or heterogeneous? Is it the same throughout or is it different throughout? With the chicken soup, that's going to be heterogeneous. We can literally see the differences. That is a piece of chicken. That's a carrot. Those are noodles. There is liquid broth in here. There are different parts of this with different properties. If you have different phases of matter mixed together, solid and liquid and gas, that is guaranteed to be heterogeneous. If you have different colors in different parts, that is all of a sign of heterogeneous. You can see the different bits. If we instead look at something like salt water, so this salt, imagine, gets put into the water, and then it starts to dissolve. That is homogeneous. And that's because we can't see the salt in there, right? We can't see that there's not more or less, right? Right now, when it's in the spoon, that's you can see. But once it was dissolved, there's the same amount of salt in the top as there is at the bottom. It's not like the top is more salty or the bottom's more salty or the left or the right. It is the same throughout. You can't, like if you were drinking salt water, you couldn't save the salty bit for the end. This is why I have to show you the handful of salt, because once you poured it in, it would look the same throughout. It would just look like water. You wouldn't be able to see that. So now if we turn to something like blood, it certainly looks like blood is the same throughout, right? It's all dark all over, right? That's all dark. But the question is, is it really still all heterogeneous or homogeneous? Our tendency would be to say homogeneous. But if we zoom in on blood, we can see that before we get to the atomic level, there are different bits in their blood. In blood, you have a liquid with little bits of solid called blood cells that are floating around in that blood, right? So those are different little bits. They are different phases. It's similar to the carrots we had in our soup. They're just really small, and they're too small for you to see, but it's still heterogeneous. So you would need a microscope to figure that out. What you can use is the fact that blood is cloudy. Okay, so for gases and liquids that you're dealing with, not solids, but for gases and liquids, homogeneous mixtures are usually clear, like the salt water. When I say clear, I don't mean that it doesn't have color. I mean that you can see through it. Okay, so you could see through the other side. It is clear. So it could be like Kool-Aid is a clear red because you can see through the Kool-Aid. Blood is opaque. You can't see through it. There is cloudiness, even if you say to lowered made it less big of a blood bag, it'd still be cloudy. There still would be that aspect. So milk, orange juice, blood, those are all cloudy. Clouds are heterogeneous mixtures because there's water, little small bits of liquid water floating around in the air. Fog, the smoke, those are all heterogeneous mixtures because they're opaque or cloudy. Again, that's only gases and liquids, but whenever we see that, that's what we want to key in on. Is it cloudy or opaque? If so, it's heterogeneous. So when we look at this idea, we want to compare and contrast compounds and mixtures. So if we take, say, salt and pepper, and we combine them in a mixture to make salt and pepper mix, this would still then be, you've retained, you don't do any sort of chemical change. It's still salt and pepper, so they still have the properties of salt and pepper. That's really good that you can control them. You can make it more salty or more peppery. You have that flexibility because it's variable composition. You can make your mixture however you want, but importantly, you maintain those properties of whatever the things are that you're mixing together. If you say combine elements, sodium and chlorine, into a compound, salt, right, where now you've made, instead of a mixture, you're making a compound, you're going to see more aggressive changes in the properties. Salt has no properties corresponding to those of sodium and chlorine. Sodium is a highly reactive metal, chlorine is a toxic yellow gas, salt is a balanced part of your diet at a reasonable amount, but it is important, you need it to live, right? And so you have this sort of balance where it's a really drastic change. When you go from elements to compounds, you get entirely new properties, entirely new everything. And so you get a lot of control, but salt is always going to be salt. There's no flexibility. So we use compounds, we make compounds to get entirely new properties, and then we can mix them together in mixtures to kind of modify or get slight changes to those properties. And that allows us to control. So both of these types of kind of classifications of matter are going to be useful. So we can put this all together in terms of overall classifications of matter. We want to think, if the first rule is that kind of mixture versus substance level, which is basically when you make it, is it always the same? Or do you have flexibility at making it? Is it uniform throughout for classifying mixtures? We can use, in some regards, especially like liquids and gases, we can use by just observations on them. Sometimes with solids, we need to know a little more about how it was made, especially for homogeneous mixtures. For pure substances, can it be simplified chemically? Generally, we have a list of elements. If we know it's a pure substance, if it's on the list of elements, which is 118 of them, then it's good. Otherwise, we'd guess it's a compound. A lot of times, if you get a technical name, we'll learn how to name compounds, but for the short term, just look it up. It'll tell you if it's a compound. Let's take a look at an example of kind of classifying overall. For each of the following, determine if it is an element, compound, heterogeneous mixture, or homogeneous substance. So this 4 options can seem daunting. We want to do all 4 levels of classification, but the thing is we don't need to go immediately to that answer. We can break up this sort of problem into 2 steps. First, we could figure out, is this thing a substance or a mixture? And then go back from that, right? We had that flow chart we just looked at. We want to use these first tools. Is it a pure substance or is it a mixture, right? Does it have variable composition or constant composition? Then, now it's a smaller question. You're determining within that level. Is it heterogeneous, homogeneous, that kind of levels? You're making the questions that you're asking a bit more simple. You don't have to jump just to the answer. First, we'll look at bread. So we want to ask the first question, pure substance or mixture, which is really the same thing as, can it be different? And there are a lot of varieties of bread. So at the point in time when there are a lot of varieties of bread, it's not always the same. Even the same, if you follow the same recipe, you might burn it one time. You might use a little too much flour one time, but you still get bread. And because they can be different, that makes it a mixture. So then the question is, what type of mixture is it? Is it heterogeneous or homogeneous? And the question then is it the same throughout? Well, bread, we know, certainly has a crust. It has the inside, right? That's 2 different regions that you could see. And so if you can see those 2 different types of regions, that makes it heterogeneous. On top of that, inside bread, you usually have air bubbles. Air, that's a gas, that is different from the solid that the rest of the bread is made out of. That's another level of difference throughout. That's going to be heterogeneous. Do you put seeds in your bread? Is there burnt spots on the bread? Are you making like a pita or flat bread where, certain parts get hotter on the grill, you get air bubbles, they get burnt, right? There's different colors even within the crust. All of those point to heterogeneous. For nitrogen, this one is going to be one of those things, that name looks pretty chemical. You may be familiar with nitrogen, but you could look it up. You could use the periodic table, which we will return to, but the periodic table of the elements, it's in your book, it's all over the place. If it's on there, it's a listing of the elements, nitrogen is there, that makes it an element. So then if we have something like methane, that sounds similarly chemically, right? But if you looked, you would not find it on the periodic table of the elements, and you could look it up and learn that it's a combination of the elements carbon and hydrogen, which makes it a compound. So mixtures, a lot of times, that is, those are the things you interact with, and so you have a lot more kind of observational experience, whereas elements and compounds are going to be more like look them up or kind of those sorts of things. Really, that's going to be what it comes down to. Air, then, if we think about that, that is the kind of thing we interact with on the day-to-day basis. So the question is air always the same? Okay. In the summer in Baytown, I think the air generally tends to feel pretty different inside of a building, inside air conditioning, than outside, right? We know that air can be different. It can be more humid, less humid. If you go up in elevation, you can change the different mixture of different things in the air. More or less oxygen is in the air. And so that makes air a mixture. You can have different versions of air. So then the question is it homogeneous or heterogeneous? Well, once you have a sample of air, say a room, right? You have a room, you're the inside of your house. Is the air the same throughout the house? If you have a building, is the floor doesn't have more oxygen or isn't more humid than the ceiling air? It's all the same. And so air is going to be a homogeneous mixture. You can make different versions of air, but once you make a sample of air, once you get a collection of air, it's all going to be the same. And so that makes it homogeneous. This idea about, kind of homogeneous, heterogeneous, a lot of that is law-based. It's a scientific law. It's the result of experiments. And so it can be kind of especially distant, sometimes like blood being heterogeneous, homogeneous. Where do you draw the line? And so the theory of atoms, we said, is meant to explain things, and it helps us explain what's going on. So we said that the difference between elements and compounds was this is one type of atom, say helium, versus water has two types of atoms, but it's only those two types of atoms. Okay, so in a mixture, you would have different collections of different types of atoms. So, and you could have, in a heterogeneous, you would have, say, a region, in this case, of, say, water, and then a region that is sand for your wet sand heterogeneous mixture. And so that makes it heterogeneous, the different regions. And we can see that what those different regions are really defined is that the mixing is not at the atomic scale. At a homogeneous mixture, say, for example, tea, you have water, you have caffeine, you have sugar, you have all these different molecules, or these different compounds. You can see they're all mixed at the atomic level. You have all of this mixing occurring where it's at the molecular level. You're at the atomic level. You don't have clusters of one compound in one side and clusters of other compounds in another side. Your atoms are all evenly mixed, whereas in the heterogeneous mixture, you have, say, your sand region and then your water region. So we can get some nice insight into that. Okay, again, no participation questions for this one. That'll start with our Tuesday videos. This material will be on the midweek one homework due Wednesday. Got a couple more videos to go. See you there.